The purpose of this lab is to study the behavior of an object with constant velocity through a real-life observational model and a computational model. Newton's second law of motion will be very relevant in this lab. The law describes how an object's velocity changes only once a net force is exerted onto it. For this lab, I have studied the behavior of an object's motion while no net forces are acting on it. To study these behaviors, I need to record the motion of an object that moves at the same speed and direction through the recording. I also needed to test these behaviors in a computational model using code. Through this data I recorded, I found that without a net force acting on the object moves with a constant velocity. For the real-world model, I used a cylindrical battery, a flat surface, and measuring tape. While recording a video, I push and let go of the battery, sending it across a table. Following my initial push, the battery had no forces acting upon it for the remainder of its path. I then analyzed the video using a software called Tracker to collect data about the battery's position at different times. For the computational model, I added pre-written code that made a distance versus time and a velocity versus time model based on the data that I gave it. I designed my data to replicate the behavior of the battery in my real-world model. After collecting the position versus time data for my real-world model, I ended up with a set of data that appeared to be linear. Due to how the rate of change in the displacement versus time data remained constant, the velocity of the battery remained constant because velocity is equal to the change in displacement over the change in time. I used the average velocity formula and the observed data to calculate the velocity of the battery throughout the entire recording. The battery was moving at 0.3575 meters per second. To replicate the behavior of the battery in my code, I altered the values of velocity update, position update, and net force. Because the velocity stays at a constant rate, velocity is set equal to the vector 0.357500. The position update is set to equal the position plus the vector 0.035750 because the graph updates every 0.1 seconds. Finally, the net force is set to the vector 0, because the net force on an object with constant velocity is nothing. With all the code in place, the end result is a perfectly linear position versus time graph and a velocity versus time graph with unchanging velocity. The observed and computational data show how an object with no net force acting on it will have a constant velocity. This idea can be explained through Newton's second law of motion. In the equation net force equals mass times acceleration, the value 0 can be plugged in for net force, and a constant positive value can be assigned to mass. This could only mean that acceleration, in this case, is also equal to 0, meaning that there is no change in velocity. The two models are very similar as they both appear to be linear with a positive slope. This is because they both reflect the behavior of an object with positive velocity. As seen by comparing the r² values, the observational model has a value less than 1, while the computational model has a r² value of 1. This is because the computational data follows one perfect line. In my collection of data, I had possible sources of error. When setting up my real-world experiment, it is possible that the battery was not rolled in a perfectly straight line parallel to the tape measure. When analyzing the video I recorded, I may not have perfectly captured the correct coordinates on the battery positions in the tracker application. What would have happened if I had flipped the x-axis in my models so that the objects would move in the negative x direction instead of the positive x direction? This action would make all my position values negative while keeping my time values positive. The rate of change of the position versus time would also be negative, meaning that the velocity of the objects would be negative. Is it possible to say how many forces are acting on the object I observed? Well, I cannot be sure of every possible force acting on the battery. There's a force of gravity pushing the battery against the table, as well as an equal and opposite normal force pushing up on the battery. There is also some friction and air resistance acting on the battery, but measuring those forces can be difficult and did not have major impact on the object during the experiment. In conclusion, Newton's second law of motion can be replicated and observed in the real world as well as in computational models. This lab shows how the manipulation of variables can lead to predictable outcomes.